Hello and welcome back. We're coming to you from the Downtown Transit Center. A few minutes ago, when the announcement was made that this presentation was going to take place in statistics, everybody left the building. Despite that, we're happy that you're in attendance. Let's continue. This is presentation 10.2, materials in your workbook, and we want to acknowledge the development team of Brad Spencer and Amanda. To illustrate the theory here, we're looking at an economic application where we have the sales demand. We want to check or test the degree to which this is correlated with the price of the commodity. So we take 8 market locations and we have the price versus sales here, paired data. And we're going to do this analysis in Excel. And this is the Excel screen. And this is the graph. You can see a downward trend here, a negative correlation. And we're going to invoke the data menu, data analysis, and upcoming the screen here is the input screen. We have the Y range, X range, and so on. 95% confidence. We're going to complete this dialog box. 95% confidence level. And this is the Excel output. We're going to focus on these two values here. The Pearson coefficient of correlation and the coefficient of determination, the R-square value. And we're going to investigate the degree to which there is an association between these two. Now, if we assume now that there's no other information given, all you have is the sales, these 6 sales figures, these 8 sales figures, and plot these in random order, you can see that they tend to jump around. The best estimate of sales demand is the average here, 64.1 thousands of units. We can regard this as the best fit line for this set of data. However, now, if we now pair it with the price of the commodity, we get quite a different situation. We see here that as the price goes up, the sales volume goes down. And the measure of that is the R-square value. And we're suggesting that R-squared represents 86.1% of the changes in sales may be associated with the changing in price. Now we're going to look at a test of the correlation coefficient rho. There's no correlation, no significant correlation between the two. Rho is equal to 0. And we're going to suggest that this is an estimate, a population parameter. So we have here the inferential aspect of it. At the sample level, we have a small case r or capital R, and the population parameter being rho, the Greek letter. We're saying assume this is 0. And otherwise, if there is a significant correlation, rho is not 0. Now the test statistic involves a t-distribution with n minus 2 degrees of freedom. We lose an extra degree by the pairing of the data, and the test statistic is given here, where r is the correlation coefficient, Pearson coefficient. And we look at the t-distribution, and we see here the test criteria. And here's the output here. We're going to use this as the r, and this is your r-square. Plug these in the formula here, and the evidence suggests, is given here, 6.093, far greater than our t-critical value. This is extremely strong evidence against H0. So we reject it. So this suggests the model is very, very powerful model for prediction purposes. Now we're going to do a test of a slope now. We're suggesting a test of a correlation and a test of slope are equivalent. And we're going to assume a linear trend here, B0 plus B1x. Refer to the 10.1 presentation for these. And we're suggesting here that B0 and B1 are estimates of population parameters, beta 0 and beta 1. And we have it there. Now going to the, by the way, x would be the independent variable and y would be the dependent variable, because in this model we would want to, given the price of a commodity, to predict the sales volume. Now here is the Excel output. This is your slope, your intercept. Putting these into the equation here, we have our regression line, or least squares line, or best fit line. The slope delta y or delta x. Change in sales demand or change in price. This is the slope here. Notice the negative slope. That's negative 9.5 1.528. And this is the average drop in sales per unit drop in price. When the price changes by $1 a unit, we can expect the sales volume to drop by 9.582, like less than thousands of units. The best prediction of sales volume when the price is $36 per unit is a matter of simple substitution, and that's given by 71.31, which corresponds to the Y value when X is 36 here. The null hypothesis now, we're going to do a test of slope. The null hypothesis is no correlation. The slope is basically 0. HA, there is a correlation, beta 1 not 0. And again, we're saying these are estimates of the population parameters. Degrees of freedom 13, and it's much the same as before, same critical values, because essentially it's the same test. And we can see this are test criteria. Bring on the evidence. The evidence is down here at the bottom. This is your B1, this is your standard error in B1. And putting that in, we get this test statistic, or T observed, 6.093. Far more negative than minus 2.477. P-value is given here as well on the lower right. And that is very, very significant. Very strong evidence to reject H0. Confidence interval coming on the screen here. Note your T critical value. There we have it. These numbers here represent the distances in the vertical distance when delta x equals 1. And that's the end of presentation 10.2. We ask you to review once again and look at presentation 10.3 or 10.2 part 2.